Hello everyone, my name is Gibor Basri, and I'm here to talk about a question that has puzzled all cultures over all time, which is, are we alone? Are we the only thing there is in the universe? Is the only life in the universe here on the Earth? And if not, what's out there? So I'm going to take the perspective of an astronomer or astrophysicist and talk to you today about what we think we know already and don't know already about that question. Hopefully everybody knows that we live on a planet in a much larger galaxy of stars. There are about 400 billion stars in our galaxy, and that means that you don't have to have a very high percentage of stars that have planets with life on them to have a lot of life in the galaxy. So I'm going to just tell you a little bit of astronomy to get you up to speed on how we're thinking about this question, including what are the most common kinds of stars for habitability? Is that stars like the sun or some other kind? Why do we think planets might be habitable or not habitable? And how many planets are there? And then near the end of the talk, I'll get into stuff that we actually don't know very much about. For example, how common might life be? And in particular, are we going to actually get contact from alien civilizations? So let me just point out that stars are not all the same. There are various kinds of stars. I'm not going to even name them here, but just to say that some of them are very hot, like 40,000 degrees. Some of them are like our sun, around 6,000 degrees. And some of them are half the temperature of our sun, like 3,000 degrees. That has to do with how massive they are. So these hot stars are 50 times more massive than our sun, and they go down to about 1/10 the mass of our sun. And more strikingly, how luminous the stars are varies even more. So these heavy, bright, hot objects are 100,000 times brighter than our sun is. If you put one in place of our sun, we'd have 100,000 times more radiation on the Earth. Of course, the Earth would melt immediately. Stars that are much less massive than the sun are a lot less luminous as well. So this one here is only 1% the luminosity of the sun, but they get even less luminous than that, 0.1%. So there's a huge range in stellar properties. On the other hand, they're not all the same amounts of different kinds of stars. So it turns out that these hot, massive stars are very rare. 0.1% of all the stars are like 10 times more massive than our sun. And the sun itself, in fact, is somewhat rare. Only about 3.5% of stars are like our sun. Most of them are quite a bit less massive than our sun, 1 or 2 or 3 tenths of the mass of our sun, and consequently fainter than our sun and cooler than our sun. So that, of course, makes a difference about if you wanted to have a planet that was habitable around one of these stars, you better know which kind of star you're talking about. Now I want to touch on the concept of habitable zone. That sounds like, well, if I put a planet there, it would have life on it. But that's not really what it means, because we don't really know much about life on other planets yet. So when people talk about a habitable zone, what they usually mean is that if you took the Earth and you put it there where this planet is, around that star, it would still have life on it. That's really what habitable zone means. That doesn't, of course, mean that the planet that's actually there is like the Earth. You don't really know that. Or in a more general sense, what we mean by habitable zone is this planet could have long-term liquid surface water on it. And I'll talk in a minute about why we care about water. But that still doesn't address the question at all about, is there life there? For example, just because you know that there's a certain planet a certain distance from a certain star, you probably need to know something about its atmosphere before you could even begin to talk about life on the planet. For example, it might not have an atmosphere, in which case it certainly wouldn't be habitable. So the question actually has mostly to do with whether the star would let the planet have a reasonable temperature given how bright the star is and how far away the planet is from it. And then, of course, that does depend on the stellar types. Now, why do we care about water? Well, there is a huge variety of life on the Earth, but no life on the Earth can do entirely without water. Of course, that doesn't necessarily mean that much about other life, because it just means that all life on Earth evolved using water. But since it's the only kind of life we know, that's what we're looking for so far. So why is water so great? Well, these are kind of technical issues, but it's a polar molecule. That is to say, it has a little bit of a charge one way or another, and that gives you useful properties like surface tension. Cells use it to sort of stay together, and protein folding makes use of that too for biochemistry. Water is a mild solvent for many kinds of interesting organic and other molecules. And of course, it's a nice medium for transporting molecules around and mixing them, as you know. You also know that water can exist on the same planet in all three forms, solid, liquid, and vapor, since they certainly all exist here on the Earth. And then here's a weird kind of fact. Water is not usual in the sense that if you take the solid form of water, it isn't actually denser than the liquid form. That's true for most elements. The solid one will sink in the liquid, but in the case of water, ice actually floats. And so that means if you have a planet with water on it and it's a little cold, the ice will form at the top of the water first, and you can still have liquid water underneath it, as opposed to freezing from the bottom up, and then you would just get a solid block of ice, or in a solidly frozen ocean. So habitable zones have those general characteristics to them, and of course, if the star is faint and you want it to be warm, you need to sidle up close to the star, which means the habitable zone size for these faint stars, the cool ones, the red dwarfs, are small. They're some size for solar type stars. They would be even bigger for stars that are brighter than the sun. But as we saw, those are pretty rare. So you do need to worry about the habitable zone size. And if you're looking for habitable planets, you need to find them within these habitable zones. Then there's the other properties that we also care about. For example, if you're in the habitable zone, is it dangerous to be there? Well, why would it be dangerous? Well, we're going to come back to this, but stars actually put out a lot of high energy radiation and high energy particles. And so if you go close to the star, unless the star isn't putting out too many, it'll be more dangerous there. So for example, around these red dwarfs, you get 400 or sometimes 1,000 or several thousand times the X-ray flux from the star that we get from our sun. So that's kind of dangerous. And yeah, here's for the sun. Another question is, and we've talked about it a bit, how common are these stars? So if they're very rare, you're not going to find very many habitable zones because you can't even find that many stars. And we've mentioned that the red dwarfs are very common. I'll say how common a little bit later too, compared with stars like the sun. And then another property of stars, which I didn't mention earlier, but it goes with this brightness thing. So you saw the masses of stars kind of vary, a factor of 10 up or down from the mass of the sun, but the luminosity is varied by a lot more than that. So that means if I have a star that's 1/10 the mass of the sun, but it's only, a 1/10% as bright, then it's going to last longer. It's using its fuel more efficiently, basically. And so the lifetime of these red dwarfs, it goes from 100 billion years up to even 1 trillion years. Now, the universe is only kind of 10 or 14 billion years old. So that means these stars live far longer than the universe has lived to date. So they're very long-lived stars. Whereas the sun, its lifetime is about the same as the universe. That means the first stars like our sun that were formed early in the universe are dying now. And our own sun has another 5 billion years or so to go. But they die comparatively quickly compared with these red dwarfs. We're also going to talk about other kinds of problems like tidal locking in a bit. Well, another fact about habitable zones is stars, it seems like the sun always shines about the same amount. And of course, on a human timescale, that's totally true. It does. But over astronomical time, the sun is, for example, steadily getting slowly brighter. And that means that if you're in the habitable zone now, you might not be in the habitable zone later when the star is too bright. And in fact, between these dashed lines is sort of the habitable zone for an Earth-sized planet around a sun-like star. And this is definitely habitable, and this is perhaps habitable in the lighter green. This is based, of course, on our own experience on the Earth. So no surprise, the Earth is right nicely in the habitable zone here. But you'll notice that the habitable zone starts moving upwards here. And these are distances from the star. So here's Earth's orbit here, but here's Mars's orbit here. And this is time. So here we are right now at 4.5 billion years. You go out to 8 billion years, the Earth will no longer be in the habitable zone of the sun. What'll happen? Well, the sun will be brighter, and in fact, the temperature on the Earth will be so high that our oceans will boil. So the habitable zone of the Earth, doesn't last forever, and in fact, we'll actually move out of the habitable zone in about 500 million years from now. People are worrying about climate change now, but that's some really serious climate change. On the other hand, if you lived around a red dwarf, you wouldn't have this problem. Remember, they live far longer than the universe. So on the time scale of the universe, they really stay pretty much the same brightness. You can be a little more sophisticated about habitable zones, and actually you kind of need to be. And this also ties into the climate change debate now, which is, let's say you have a decent atmosphere around your planet, but what's the greenhouse effect on that in that atmosphere? That matters. It matters for climate change here on Earth. And in fact, the Earth has had rather larger climate changes in the past than we're going to get this time around. And life has survived, but life also had to change quite a bit during those times. But as you fiddle with the greenhouse effect on a planet, you can take a planet and freeze it completely if you remove the greenhouse effect. So for example, the Earth is actually too far from the sun now to have liquid water on its surface unless it has a greenhouse effect. And in fact, the main greenhouse gas on the Earth right now is water, the water in our atmosphere. So we would freeze over completely were it not for the water in our atmosphere. And in fact, the Earth has frozen over in the past. It didn't go too far because volcanoes replaced enough carbon dioxide. But if you're talking about some other planet, it might get frozen and stay frozen. On the other hand, Venus is a planet that's pretty much the same as the Earth, or was to begin with. Excuse me.
Gibor, can I interrupt for just a moment?
Sure.
There's a tiny box that's on your screen that is your formatting box. If you can just close that, that would be super helpful. Perfect. Wonderful. Right. Thank you. So please carry on.
I didn't see the little box. Okay. So let's see. We were in the middle of talking about greenhouse effects. And I was just about to talk about the planet Venus, which is a planet very much like the Earth, about the same size, probably started with pretty much the same composition, but it was a little closer to the sun. So it was experiencing at the beginning what we're going to experience in 500 million years. Its oceans were boiled, and that put all the water in the atmosphere, which gave it a strong greenhouse effect. And then the sun basically destroyed all the water on Venus and stripped it off. And Venus was unable to take its carbon dioxide and put it into the rocks. So almost all the carbon dioxide on the Earth is in our rocks. The stuff, the fossil fuels we're talking about now, is a tiny fraction of all the CO2, whereas Venus has that all still in its atmosphere. So the pressure at the surface of Venus is 90 times our pressure, and the temperature on the surface of Venus is 800 degrees. It's worse than a self-cleaning oven. And that's all greenhouse effect, basically. So if you're talking about a planet that you don't understand its atmosphere, you can see, you probably can't really guess whether it has life on it or not. Although I suppose I should mention that in the news last week, there was a discovery of a molecule in the atmosphere of Venus, which, at least on the Earth, is caused by life. So people started talking about, well, okay, the surface of Venus is certainly inhospitable, but maybe there's life, 30 kilometers above the surface. Don't know. Does goes to show, though, that we still need to learn a lot about life on other planets. Okay, let's see now. How do I advance my slide? Not sure how this particular mode works to advance slides. Did I get the window back, or am I still good?
You're good.
Okay, great. All right. So let's move on now to talk about why stars can be dangerous for planets. And that basically has to do with the fact that stars produce magnetic fields on their surface, especially stars like the sun or lower in mass than the sun. So here are 3 pictures of our sun. This is what it looks like in visible light, which is pretty uninteresting. You see a few dark spots on it, and those are places where the magnetic field is strong and makes the surface cooler. But as you go up in the solar atmosphere using a physical technique, this is above this visible surface of the sun. You see it gets a lot more interesting looking. And these bright patches here are all places where the magnetic field is stronger. And you go into the X-ray band and take a picture of the sun in X-rays, and you see that it's surrounded by a hot atmosphere. This atmosphere is 1,000,000 degrees and emits X-rays at the Earth, and that can be an issue for a planet around the star. And in our case, of course, it's obviously not deadly for the Earth. So here are some other pictures of the sun, but other stars, the sun is actually relatively inactive. So other stars can be far more magnetically active than you're looking at here. Here, this is also an X-ray picture. You can see that the atmosphere above the surface of the sun is controlled by magnetic fields that will give you all these loops. These are huge structures. So here's the Earth to scale around one, and here's some of these loops. And sometimes the loops get disrupted and blow out. And you get a kind of an explosion, and the sun blows off a huge amount of material like this. So this whole bubble here is being blown off towards the planets, and there's a lot of high energy protons and so on in here. And sometimes that hits the Earth. Now, in the case of the Earth has a magnetic field, and that magnetic field also causes the gas to stream, but now it streams around the Earth. And so we're protected from most of those effects that the sun is trying to hit us with. But you could have a planet which didn't have a magnetic field, or as I mentioned earlier, if you're around a red dwarf, you need to go much closer to the star, and then your shields just might not be adequate, or you might not even have them. And the star can actually begin stripping off your atmosphere. Plus, these explosions are full of high energy radiation, X-rays, gamma rays, high energy protons. So none of that's good. We're far enough away from the sun that it really doesn't hurt us. Although if we get hit by a big one now that we have all these satellites orbiting the Earth, it might take them all out. So people are worried about that. But at least they're not worried about losing our atmosphere. Red dwarfs can have far more energetic flares than the sun does, up to 1,000 times more energetic, and you go much closer to them. So you can see that that's really actually an issue for habitability around red dwarfs. In fact, even in our solar system, this effect of the star has played havoc with 2 planets. One is Mars. So Mars has a very thin atmosphere. That's partly because it's a smaller planet and has more trouble hanging onto its atmosphere. But if the sun weren't constantly stripping it, it would have much more atmosphere than it actually does. And indeed, we have a spacecraft around Mars right now that's measuring how much of Mars's atmosphere is being stripped off by the sun essentially all the time. So that's the main reason Mars has a very thin atmosphere. And Venus, as I mentioned earlier, used to be much more Earth-like. And the problem with Venus is you have all this ultraviolet and X-ray radiation coming from the sun. You have the water not in oceans, but up in the atmosphere, and it's hit by this radiation, which breaks the water into hydrogen and oxygen. And then Venus doesn't have a magnetic shield up, and so the solar wind just strips the hydrogen off of Venus altogether. And of course, if you don't have hydrogen, you can't have water. And so that's really what happened to Venus and why it's completely uninhabitable, at least at its surface today. So when we want to talk about other planets, we would want to know things like this. And at the moment, we don't know other planets well enough to really answer these questions. So in particular, you may have in the newspapers over the last 2 or 3 years heard several announcements where we've discovered planets that are seemingly Earth-sized in the habitable zones, but of red dwarf stars. Essentially all the announcements of Earth-sized planets in the habitable zone refer to nearby red dwarf stars. And so I'll explain a little bit about why that is, and then we'll talk a little more about, okay, those planets are in the habitable zone, but could they be habitable? So I said earlier that there are a lot of red dwarfs. In fact, really 3/4 of all stars that are ever made are red dwarfs. And they all live far longer than the universe, so they're all still here. So red dwarfs are definitely the most common kind of star. We also have found that smaller stars tend to host smaller planets. And by smaller planets, we mean planets like the Earth. So, so actually, most of the stars in our neighborhood are red dwarfs, and they have the more Earth-sized planets. And consequently, this statement is true, that essentially all the habitable Earth-sized planets near us are around red dwarfs. So we want to understand that better. One reason for it is not that they're the most common, although they are, but they're also the easiest to find. So we use 2 basic techniques to find planets. One is the planet pulls on the star, and we can kind of see the star getting pulled. And if the planet's closer to the star, it'll pull on it harder. So planets in the habitable zone around red dwarfs pull on them harder. And the red dwarfs, remember, are also smaller, so they can get pulled more. So we see more of a wobble for that situation. The other way we find planets is they just block light as they go across the stellar disk, if they happen to be lined up that way. And the amount of light they block depends, of course, on how big the star is. If it's a smaller star, they'll block more of its light. And that means red dwarfs are easier to find Earth-sized planets around for that reason. And then finally, the habitable zones around red dwarf stars are close in. That means that the planets orbit them more quickly. And so we see all these effects on, on an easier time scale. Instead of taking like a year, like the Earth does to go around the sun, it might only take a couple weeks for a habitable planet to go around a red dwarf. So it makes it easier to find. Unfortunately, there's a downside to that, which is these planets are so close to their star that the situation is like the Earth and the Moon, in that we have tidal locking. So probably you all know that the Moon keeps the same face towards us all the time. We only see one side of the Moon, and that's because it's this kind of situation. So if you're standing on the near side of the Moon, you're always pointing towards the Earth. If you're standing on the near side of the tidally locked planet, the star is always up. So one side of this planet always has day, and the other side always has night. That's what tidal locking will do. And that's what happens in the habitable zones around red dwarfs, because they're close enough to the star that basically the star distorts the planet into a bit of an egg shape, and then the egg ends up pointing at the star. So just like with our Moon, that's the situation. So there's never a sunrise or sunset. One side is heated by the star, the other side never sees the star. And of course that would have a big effect on the planet's climate. and probably its habitability. And in fact, astronomers until 10 or 20 years ago thought that no planets around red dwarfs would be habitable, because if they're in the habitable zone, the dark side never sees the star. It gets so cold there that the atmosphere freezes out onto the surface, and then of course the rest of it would come around and freeze out as well, and you might not have an atmosphere anymore. Turns out that doesn't happen actually. So luckily, luckily, even if you have an atmosphere like the Earth, this is a temperature map of a tidally locked planet. Basically, tremendous jet streams develop and carry the heat around to the backside enough that the atmosphere doesn't freeze out. Now, of course, on the Earth, we have a situation where Antarctica doesn't see the sun for 6 months, and it's pretty cold. And so you can imagine that the night side of these locked planets would be even colder. So they'll be pretty much frozen, totally frozen, always. But that doesn't mean you can't have life, for example, under an ice cap, because remember, ice floats, and you won't freeze out the atmosphere. So we still include them as potentially habitable. So the real question right now is this magnetic activity question. That is, does the star, is it going to strip the atmosphere off the planet due to the magnetic activity? Not that it would freeze on the back, but the star would just bombard the planet with high energy protons until it didn't have any atmosphere left. That's one question. And to answer that question, we really need to understand planetary magnetic fields better, and we don't really at the moment, so that remains a question. And then the other thing is, are the planets going to suffer the same fate as Venus? Are they going to lose their water while the star is settling down onto its stable characteristic? And then a secondary question, which I don't think is actually very important, is does all that high energy radiation actually, harm if there were life on the planet, does that kind of, cause it to mutate? Remember, you can put UV lights in your room and kill all the COVID. So now you got a tremendous UV light here. Would that kill everything on the planet? Probably not. I mean, for example, you could live, if you're around a red dwarf, you could just, live where you can't see the star. That would certainly save you. Or if you live under a couple feet of water, that's also not going to be a problem. So we're thinking about this water problem, and there's various ways to solve it, even if the star strips the water off the planet to begin with. One would be just store water under the surface, wait a few billion years, and then bring it back out through volcanoes. And remember, with red dwarfs, you got all the time you need. The planets live forever, basically. Another idea would be maybe you can resupply the planet with water after the star stops being so active. That would mean hitting it with a bunch of comets. Of course, you wouldn't want to be around while that was going on, but after that was done, maybe you could get water resupplied. And of course, any water that ends up on the backside of the planet will freeze down onto the surface and be protected. So yeah, you could get a supply of water again. Another possibility, which we actually see evidence happens, is you can actually move the planets around in the system. So you could keep the planet away from the star while the star is too active and then bring it in later, maybe. That would be pretty contingent and not as common, obviously. But it does happen. We see it happen. Or finally, maybe you can make the evaporation actually work for you. So we actually find that there are many, many planets that are somewhat more massive than the Earth, and they have an envelope of hydrogen and helium around them that's a few percent the mass of the planet. That makes those planets uninhabitable. But if you put one near, right near a red dwarf and let the red dwarf strip that off, then at least sometimes you might end up with just the right amount of hydrogen at the end. So that's another way to solve this problem. But my point here is that we find Earth-sized planets in the habitable zones around red dwarfs. We don't know that they're inhabited by any means. And actually, the very nearest star to us has such a planet. There's a planet that's at least 1.3 Earth masses orbiting this red dwarf, Proxima Centauri, which is the very nearest star to the Earth, about 4 light years away. So it's very close in. It's in the habitable zone of Proxima Centauri. Here's our solar system, Mercury, Venus, Earth. But remember, the star is much fainter, so this is actually in the habitable zone for that star. We don't actually know how big the planet is because we only found it by wobble. So it's all speculation right now about what kind of planet that is. But here's another system around a nearby red dwarf called TRAPPIST-1. And this one has 7 planets, all essentially well within the orbit of Mercury. Consequently, several of them are in the habitable zone of that star. And we've actually detected water on a few of the ones that are larger in this system. And 3 of them are kind of Earth size and kind of in the habitable zone. So this is pretty interesting. This is a very interesting system. The star is very dim. It's going to live for almost 1 trillion years. And we hope to actually be able to study these planets more in the coming decade or so. Okay, let me finish my talk by talking a little bit about what's the likelihood that we're going to have contact with extraterrestrial civilizations. That question, let me just hit the punchline first. We don't have any idea, but we can start to guess at it, and we do so with something called the Drake equation. Don't worry about the fact that it's an equation. I'll just go through it. But basically, you can calculate the number of civilizations that we could detect with radio telescopes, because that's how we're looking for them right now, as the rate at which such civilizations appear times the lifetime of those civilizations. And the rate at which they appear is a set of these factors here. So the rate at which stars appear times the probability that the star is a planet times the probability that the planet's habitable, and so on and so on. So I'll go through this quickly. The first 3 factors are astronomical, and we're fairly far along on those. So we know the rate at which stars are formed in the galaxy, and in the last decade or so we have learned what is the probability that a star will have planets, namely just about 1. It looks like almost all stars have planets, so great. And times the probability that a planet will be suitable for life. Right now we mean will be in the habitable zone, and that's also high based on actual data. So the next 2 factors really come from biology, and that's where we're in more trouble. So what's the probability that bacteria will arise on a suitable planet? Well, the only thing we know about that is they arose on the Earth soon after the Earth was a suitable planet. And then what's the probability that bacteria will evolve into complex life? Well, the only thing we know about that is the Earth had bacteria on it for 3.5 billion years before it evolved into complex life. So apparently that's not quite as easy as just getting life on the planet at all. And then the last 2 factors are really from sociology, and those we have no idea. So what's the probability that if you had complex life, it's going to send out radio signals? Yeah, hard to guess on that one. And then how long will it do so? How long do these radio sending civilizations last on average? Obviously, we have even less of a clue on that, although, right now the behavior of humans on the Earth is not particularly optimistic on that score. At any rate, you can take your guesses at these. So here I've been optimistic. I saw these 3 things are really observed here. I'm going to say that it's if you have a habitable planet, there's a 50% chance that bacteria arise on it because it happens so quickly on the Earth. Oh, that's this one, right? This is how many habitable planets there are. So this is data here. This is a guess. Complex life, well, maybe only 1 in 10 planets that have bacteria on them evolve complex life. That's a guess, but that's sort of the fraction of time it took on the Earth. And then how many forms of complex life send out radio signals? Yeah, now we're totally guessing here, right? So I'll say 2%, but you can pick your own number there. But if you pick all these numbers, what you get is that the number of civilizations broadcasting radio today in the galaxy is the average lifetime of such civilizations divided by 100 years. So That means that if civilizations typically last for a few hundred years broadcasting radio, which looks like there's a reasonable chance humans will, at least, then this number is larger than 1. So there's perhaps somebody out there broadcasting radio right now other than us. But it turns out L has to be something like 1 million years in order that the nearest civilization is within 1,000 light years of us. So are humans going to broadcast radio for 1 million years? Well, nobody knows, but that doesn't seem like a sure bet at any rate. And the reason for this is the galaxy is a very big place, and it's been around a long time. And so as civilizations arise, and die again, you want them to be around now. So you have to have enough that there's some around now. That's the basic reason why this thing comes out this way. And this is the optimistic scenario, remember. So we are listening. We have various telescopes on the Earth that are actually searching for signs of intelligent life through radio waves. But if I take a less optimistic point of view, let's say that only 2% of planets are actually habitable, and then only 1% of those actually have life starting on them, and only 1% of those have complex life. And the complex life hardly ever broadcasts radio. Then you get 100 million years here. So unless civilizations typically last for 100 million years, we're the only one right now. So it's not difficult to come up with the conclusion that humans are the only civilization broadcasting radio in the galaxy right now. But the truth is we don't know, and I will leave you to make your own guesses. Thanks for listening.